Thank you very much. Oh, maybe we should turn down the volume somewhere, or is it okay? Or too loud? Okay. Okay, so welcome everyone. And yeah, thanks a lot for the invitation, by the way, so it's a great place to be at. This is the title that was given to me by the organizers, and I kind of assume that, everyone has heard about the fact that dark matter exists. Anyone has not heard about dark matter? Okay, very good. Anyone has not seen the like the cosmological line element in GR, like Friedmann-Robertson-Walker metric? Also very good. Great. So this is roughly what I assumed. But then, so you have not seen, or? Oh no, sorry, okay. Okay, so then if you've already heard something about dark matter at least, then after reflecting about it, you will also have noticed that, of course, there is a lot of discussion about dark matter. There are many observations. But actually, if you really want to pinpoint it, there's not so much that we actually know. Yeah? So in some sense, you can argue that the one thing that we do know is the dark matter density today. Yeah? So this is an, if you wish, actual measurement. It's based on many measurements over all cosmological distance scales, but you can all boil it down to one number. So there's one number that we know for sure. And by for sure, I know, I mean two things. Yeah, so first of all, it's certainly non-zero. Yeah, so that is established beyond any doubt. Yeah, from many, again, observations over many distance scales, ranging from galactic scales to the entire size of the observable universe. And the other thing that is also interesting to note that this parameter here is determined to a very good precision. Yeah, so it's roughly 1% accuracy or so. Yeah, so it's really, one of these examples why we talk about precision cosmology. Yeah, so that's really how you should think about this. Is of course not something that we measure directly. It's a parameter that we fit to the model, to the standard cosmological concordance model. So in other words, we have one parameter or one lambda CDM parameter to fit all observations. Yeah, and this is something that one should have in mind when you see these kind of claims here. So this one is basically independent of the modeling. Yeah? It's very hard to get around the fact that dark matter exists. The statement that we know this to a % accuracy already does depend a bit on the model. Yeah? So for example, if you model dark matter by not just one parameter, so basically the co-moving density that we observe today, but allow it to vary. So if you just say that, okay, dark matter could somehow be converted to some invisible form of dark energy. Yeah, clearly, if it's a visible form, then there are other constraints. And this happens during matter domination, then the accuracy to which we know this parameter is only 10% or so. Yeah, so this could be dark matter decaying, this could be some form of other transformation of dark matter, for example, primordial black holes, where that coalesce and then transform part of their rest mass to gravitational waves. You know, even if you make a very general assumption, this is something like 10%. But of course, if you have this kind of conversion happening earlier in the universe, where matter and therefore also dark matter only made up a tiny fraction of the universe, there can be much larger variations. So just to keep in mind, if you fit everything to with one parameter, all observations, A, the very interesting conclusion is that it's actually possible, but B, conclusions like that rest on that model assumption. Okay, so this is, in some sense, the one thing that we really know. We can pinpoint everything to one number. But then there are, of course, many constraints. Yeah. So, for example, on how cold dark matter must be. Yeah, so you know that if dark matter was not relativistic, we would get into trouble with structure formation. Yeah, would basically, by free streaming effects and the like, we would the dark matter particles moving too quickly would move out of overdense regions and wash out density perturbations, and thereby structure at small scales like dwarf galaxies, which we certainly do observe. Yeah, but also even earlier probes. So if dark matter was relativistic during the times of Big Bang nucleosynthesis, this would contribute to the radiation energy density, yeah, and thereby drive the expansion of the universe, so contribute to a larger expansion rate, and therefore basically become inconsistent with BBM. Yeah, so that's a relatively strong constraint. Yeah, then, of course, we also have strong constraints on visible interactions. So interactions with visible matter. Yeah, and this is something I will get back to. Yeah, there are all kinds of different experiments actively looking for dark matter particles. And so far, unfortunately, we haven't seen anything, which is the main reason why we can describe everything by one number. If we had seen any kind of signature that is beyond just gravitational, then we would know more about dark matter. We would know, for example, the mass scale or the energy scale. We would know some couplings maybe to ordinary matter, rates, and the like. But then there are also surprisingly strong constraints on dark matter interactions just with itself. So interactions with invisible, yeah, or you can say dark sector matter. Yeah, so this can be dark matter self-interactions. Yeah, so dark matter particles interacting with each other, not only via gravity, but actually by some particle physics processes, via some mediators, for example. It could also be dark matter interacting with some form of dark radiation. Yeah, all this is heavily constrained, both from direct observations affecting structure formation, but also dark matter production. Yeah, so if there was other stuff around there that we just don't see because it's not charged under the standard model gauge groups, it would still impact how dark matter is produced in the early universe. And well, if there's too much dark matter produced, then it would be in conflict with this one number that we know of. So the upshot is that even if you take into account all these constraints, certainly we have learned a lot, but somehow depressingly, just vanilla dark matter, vanilla CDM, still provides a surprisingly, or you can say depressingly, good fit to all the data. Yeah, so therefore, I would argue that whenever you talk about a particle model, yeah, so referring back to this particle dark matter caption here, you should at least be able to provide and give a reason for this number. So every model of dark matter, yeah, so not just claiming, okay, dark matter is a particle and it happens to have this density, but if you actually claim to have a model of dark matter, it should come equipped with a mechanism that allows you to calculate this number. So it should allow to predict omega dark matter. And ideally, because it's not only that we know this number, we actually know this number very well. Yeah, so ideally, you should have, in your theory, a way to calculate the dark matter density with a matching accuracy. Yeah, so that's sort of the introduction for how I want to organize these lectures. So by particle dark matter, yeah, I put a big focus on the subtype and how to produce it. Yeah, because that's really the one thing we really know about it. Okay, so the way I want to organize this is as follows. Yeah, so I will start with ways of producing dark matter from the thermal bath, from the standard model plasma. And of course, I will start with the standard freeze-out process that I guess most of you have seen in some form or the other before. Yeah, so this will introduce what has long been, or for quite a long time been, the most often discussed dark matter candidate, namely a weakly interacting massive particle. But I will also try to discuss aspects that are not that often discussed in this context, in particular with reference to not only the chemical freeze-out. So freeze-out refers to the point at which the co-moving number density of dark matter particles does not change anymore, but also discuss kinetic decoupling. So dark matter particles, even after this chemical freeze-out, are kept in local thermodynamical equilibrium with the heat bath until much longer. In other words, they continue to follow a thermal velocity distribution. And this has impacts on structure formation and provides, in principle, a, you can say, orthogonal observable to this dark matter relic density. So then I will discuss freeze-in, which is kind of the opposite, where you have dark matter interactions with the standard model that are so feeble. So the corresponding dark matter candidate would be a FIMP, a feebly interacting massive particle, that they never reach thermal equilibrium with the standard model, with the thermal bath. But still, it's a very sort of generic mechanism to produce dark matter with the right abundance. And then, just maybe a word about names. So I was careful here to call this production from the thermal bath. So typically, most people would not call both of these things thermal production. So this is typically referred to as thermal production, while this, for some strange reason, is referred to as non-thermal production, even though it's production from the thermal bath. Because later on I will actually talk about non-thermal production mechanisms. Okay, and then I will also mention some alternatives. So this is something that has been discussed quite a lot more recently. Going beyond these simple paradigms, alternative ways of how you can produce dark matter in the sense of how you can more or less generically generate the correct dark matter density, the one that we observe today, from interactions of dark matter particles with the thermal bath. So keywords, if you've heard that before, are, for example, strongly interacting massive particles, but also dark matter from, well, you can call it exponential growth or pandemic dark matter. So that's quite fitting. I will get back to this. And of course, my enumeration is wrong already. So it's like this. And then we will get to truly non-thermal production. And there, the main mechanism that is discussed is the so-called misalignment mechanism. So this is the standard way of how you produce axions or axion-like particles in the early universe. Again, a mechanism to potentially give you the correct relic density, but that is not at all connected to interactions with the thermal bath. It's something very different, basically related to some kind of phase transition, so a light field that acquires a potential, and then the way the potential evolves of a scalar field in an expanding background produces something that actually has the same properties as a cold dark matter particle. Then I will, so here, up to this point, we will in any case get, and then it's a bit of a question of how much time we have at the end and how long the coffee breaks take. So my plan is to at least mention gravitational production. Yeah, so this is what happens also during inflation. Yeah, so you know that during inflation, ordinary matter is produced. So in the same way, you can produce dark matter, even without particle physics connection, particle physics couplings to standard model particles, directly during inflation, during reheating. And this is also something that has produced quite some interest in recent years. And interestingly, there's actually sort of a limit in which this gravitational production, purely gravitational production, can be understood with the methods that we will talk about here. Yeah, so very concretely, when you hear about gravitational production, it's of course you produce particles in an expanding background, so in a curved space-time environment like during inflation. But there is some limit in which you can actually understand this production as something that happens via the exchange of individual gravitons. And I will try to comment a bit on this, because in particular, if you produce very light particles, you get actually exactly the same results. And this is not at all obvious, because it's conceptually a very different picture. And then finally, I want to, kind of half leave this aspect of dark matter, also because it's so much discussed these days, and maybe talk a little bit about primordial black holes. Yeah, so just in case I don't actually make it because I don't have time, I want to at least motivate why I think it belongs here. Because there's this one extremely misleading statement about these dark matter candidates, that these are dark matter candidates that don't require any new physics. Yeah, so the argument goes as follows: well, we've observed black holes, we know GR, so these are perfectly natural candidates, and we don't need any new physics, any beyond the standard model physics to explain dark matter in this way. And that is completely wrong. Yeah, so you really need quite significant new physics. Yeah, you have to introduce some strange new scalar fields with strange potentials in order to produce primordial black holes in a way such that you match this one. Yeah, no one doubts that you would produce primordial black holes in the early universe, but to produce them in the right amount, this actually requires new physics. Yeah, so new particle physics, and that's why I think this belongs here as well. Okay, good. So let's start with the first part. Okay, yeah. Okay, so in order to talk about thermal production, we first need to talk a little bit about Boltzmann equations. Yeah, so I guess most of you have seen the Boltzmann equation in a cosmological context in one or the other form. But we will need it quite extensively, and also will spend some time of the exercises on exploring the Boltzmann equation. So let me introduce it. Yeah, so in abstract form, the Boltzmann equation is just the following. Yeah, so it just states that the Liouville operator acting on the phase space distribution of some particle species I is given by the collision operator. Yeah, so basically, you want to use this equation to solve for the phase space distribution of all the species I, meaning that in principle you get some complicated coupled differential systems of differential equations. Okay, so let's first look at the Liouville operator. Yeah, so in classical mechanics, this is just the total derivative. Yeah, so and in the absence of any collisions, yeah, so no collisions, no scattering processes, only background fields, potentials, and the like. Yeah, Liouville's theorem says that the volume in phase space is always the same, is conserved. Yeah, so that means that the total time derivative of this object must be 0. Yeah, and now we want to generalize this to the case of an expanding background geometry. So we have well, of course, then you know that in GR you can't use just time because that's just a coordinate. You can always redefine your coordinates. So basically the generalization is to some affine parameter. Okay, so that means that if we have keep in mind the dependence here, yeah, so we have a dx mu d lambda d, let's write it like, yeah, let's write it like this. Plus d pi d lambda df dpi. Yeah, so of course, if you look at this from a GR or special special relativities perspective, it's somewhat strange that here you only sum over the spatial parts, while here it looks actually like an invariant. And of course, the reason is that we consider real physical particles that must satisfy the on-shell condition. Yeah, so in other words, the energy of a particle is not an independent quantity. It's just a function of, well, a constant, namely the mass, and the free momenta. Yeah, so that's why there's really no mu here, but only a sum over the spatial parts. While there can be an explicit time dependence through, for example, the metric dependence. Okay, and that's also one of the reasons I want to do this in slightly more detail. There's a confusion in the literature as to what these here actually are, yeah, and these momenta. And the way it is written, and that's where the confusion originates from, it's arbitrary. Yeah, so it's a convention. You have to choose. You have to say what you mean by these momenta here, and therefore these. Yeah, you can write this in any reference frame, of course. Yeah, and the standard choice is that you use so-called physical momenta to denote, to be the arguments of the phase-space distribution function. So the pi are these physical momenta. Yeah, so that means that, well, of course in GR, the momentum is always defined as the time derivative of the coordinates. Yeah. So I basically have to say what coordinates I mean, and that's often not spelled out. So these momenta are the coordinates of a locally inertial system. Yeah. So these are basically free-fall coordinates. Yeah. So in free-fall, these are the coordinates, the momenta that you get in free-fall coordinates. Yeah, so, but then on the other hand, if you take general coordinates, yeah, then let's call them p bar. Yeah, so if these are arbitrary coordinates, yeah, then you know that, well, they are related by a coordinate transformation. So we just have to write them like this, yeah, in order to relate to our free-fall coordinates. Sorry, this is a p mu just. Yeah, so just, since these are actually vectors or tensors, that's how a tensor transforms. Yeah, so how do we find these? Well, we can actually just read them off from the Friedmann-Robertson-Walker metric. Yeah, so you know that this is a rank 2 tensor, so you know how you get this from the metric for a freely falling system. Yeah, so remember, these are the free fall coordinates. So we just have like this. And then you realize that, well, if you take the Friedmann-Robertson-Walker line element, and this is just the Minkowski metric, you see that this is also diagonal. The time components are the same, and the only difference is the scale factor. So you can basically, by direct comparison, see that the dx0 is just 1, and dx for the spatial components is the scale factor. Scale factor to the -1 because I was considering here the inverse metric. So that means that, like, these are the coordinates, because that's what we want to use in the next step. These are the momenta that satisfy the geodesic equation. You can't, use threefold coordinates for the general form of the geodesic equation, but these are the momenta that you want to use, and they are related to the ordinary momenta by the scale factor. So now don't confuse this with co-moving momenta, because that would be exactly the other way around. So the physical momentum redshifts like with the expansion of the universe. So the physical momentum redshifts like 1 over a. So the co-moving momenta you get from the physical momentum by multiplying with a. So this coordinate momentum is given with a negative power of a. Okay. So then finally we can expand this equation here. So now of course we want to evaluate this for a Friedmann-Robertson-Walker background. So in a Friedmann-Robertson-Walker background, because of isotropy, this one, we don't have actually independence on x. Space is the same everywhere. So there's no explicit x dependence. Well, it's homogeneity rather than isotropy in this case. So f is a function of p and t. But we still get the first term here. So that's a dx naught d lambda. And let's now choose the eigentime as our affine parameter. So then dx naught dt, that's just the energy, so p naught. So we have an p naught dtf, that's the first term here. And, well, then we get these terms. So we have a df dpi. And then you see that we have these momenta here, and we take the derivative with respect to tau. So if you bring the a to the other side, that gives you two terms. So we have an a dot p pi plus an a p dot. And that's why I've been doing this. This is the expression for which you can use the geodesic equation. So this one here is minus gamma I rho sigma p rho p sigma. And then you just have to evaluate the geodesic, the Christoffel symbol for the Friedmann-Robertson-Walker background. And then you find basically, so this is related to the Hubble rate. It's a dot, and then you find, sort of by chance if you wish, that these two terms are similar. And then at this point, it's just algebra, and you find p naught tt plus minus acting on f. So the reason I've I mean, I went through this derivation is to really just remind you of what these momenta here are, the P's. Yeah, that these are the physical momenta, and so that means the momentum measured by a freely falling observer in free fall coordinates. Yeah, and that's important for the interpretation here, because, for example, if you express the phase-space distribution function in terms of co-moving momenta, then you can do the math. I mean, it's just a coordinate transformation. Then this term here would just disappear. So then it would just be a time derivative acting on f. So when you state the Liouville operator, you have to actually say what are the coordinates or what are the independent variables of the phase-space distribution function. And there's a Hubble rate obviously missing. Okay. So then, I mean, we will get back to this formulation in phase space, but most often you were interested in looking at the Boltzmann equation, and therefore the Liouville operator, for the number density. So we basically want to integrate the phase space density and the entire equation over all momenta, and then we will get a Boltzmann equation for the number density. So for number density, then we can define the integrated version of the Liouville operator. We can remember the Boltzmann equation. So let's integrate it on both sides, but we can define the integrated version of the collision operator. We will get back to this as the integral over all the momenta. So motivated by this result here, we first divide the Boltzmann equation by E, P naught, and then integrate over all momenta, and this is the number of internal degrees of freedom of the particle that we want to describe. And that should be the same, according to this equation, as the integrated version of this one. So that means that we have a d3p 2.3 and then a dt minus hpp f. Okay. Good. But this one we can easily evaluate. So you see that t and p are independent variables for the first term, so I can just pull this time derivative outside of the integral. And what remains then is a phase-space integral over, or a momentum integral over f, which is just the number density. So the first term just gives me the time derivative of the number density. And then I have the second term, so minus h g d3p 2 cubed, and then a p and the divergence acting on p. Now this one I can solve by partial integration. So I basically shuffle this derivative, this divergence here, to the left. So first of all, if the derivative acts on the entire expression, so p times f, this will give me a total divergence. That means I have a volume integral over total divergence, so that's a surface integral. And since I'm integrating over all of space-time, the surface terms are at the boundary of the observable universe, so they don't contribute. So that means I only get the other contribution. So I can replace this with this here, which is just a minus 3. So that means here I get n dot plus 3h n. Because once you've done this, it's again just an integral over f. And this is typically the form of the Boltzmann equation that that you find in textbooks. Yeah, so let's take a slightly closer look, because now we actually have to evaluate the collision operator. Sure. Sorry to interrupt you. I should really say thanks a lot for interrupting me, and it should not only be Nicolau who is doing this. Yeah, so and especially if you think that I'm talking too fast, just feel an even stronger urge to interrupt me and ask questions. So, yes. Yeah, but this is just, of course I wouldn't have to do this. I just did it in this way because then this argument becomes simpler. Yeah. Exactly, just for distinction. Of course, like strictly speaking, it doesn't make any sense to write it like this because, of course, in Friedman, Robertson, Walker, you actually do not have this form, but actually just this, right? Because it's actually isotropic. Yeah, but in this derivation here, you don't have to make that assumption. You can still keep it as an arbitrary p-dependence, yeah, and then you get this result. Yeah. And then that's easier for me, exactly. And that's why I wanted to keep it in this form. Yeah. But of course, the result will be the same. Yeah. Okay, I should maybe stop and ask, are there any other questions at this point? So probably it's also the kind of thing that you have seen before, with the exception maybe of a discussion. So at least I remember that I was grossly confused about like what kind of momenta enter into the game, because we have physical momenta, we have coordinate momenta, and we have co-moving momenta. Yeah, and it's important to keep them separate and know at which stage they're entering. Okay, so maybe there will be more questions later on. Okay, so let's look at the collision operator. And, well, for simplicity, we will look at 2-to-2 processes. So 2 initial states and 2 final states. And then let's say that we have one ingoing particle for which we want to write down the Boltzmann equation. So let's call the form momentum E and P. And then the others we call K with energies omega. So then our collision operator, again at the phase space level, is an actual phase space integral over all these 3 particles. Okay, let me write it like this. So I have over 2g, and g is again the number of degrees of freedom of this particle p here. And so I have a d3ki 2 pi 3 to omega I. And then I should enforce momentum conservation. So P plus K1 plus K2 plus K3, like this. And then it's basically an ansatz that tells you what is the probability of this process to happen in that direction. Yeah, so that depletes the phase space density of these particles that we want to consider. And what is the probability of a process happening in that direction, which gives you more of these particles. So that means that we use the amplitudes. Yeah, and in this convention here, you always have to be a bit careful once you start to look at the details with these internal degrees of freedom and phase space integrals. Yeah, so you have to keep track of symmetry factors and so on. So in this convention, this probability amplitude here, squared, is summed over all both initial and final state degrees of freedom. Yeah, that's again mostly just a matter of writing. It's the most economic way of writing, because if you write it in terms of the standard averaged amplitude, you have to keep track of explicit factors of G for all these factors, particles as well. Okay, so then let's check. So for this process here to happen, yes, this comes with a plus sign because it produces these particles. Now, this is proportional to the phase space density of these guys. So let's write it as F2 and F3. Yeah, but then you also have to take into account quantum statistics for what is the final state in that direction. So we have a 1, minus, or plus, depending on whether these are bosons or fermions. F1 and 1 minus or plus, just F without a subscript. Yeah, that's what we used for this particle. Yeah, so just to remind you, like if the final state particles are fermions, yeah, then of course there's a suppression. You can't produce arbitrarily many of them because every quantum state can only be occupied once, and that's the origin of this suppression factor. While on the other hand, if they are bosons, you can in principle get enhanced processes because you're driven into a state that resembles a condensate. Okay, and then the opposite process is this one here. So we have an F1, F times 1. Okay, so let's already introduce this notation here. Yeah, so these factors I will denote just with an F bar. So this is F1 bar, quantum statistical corrections. So you have F1, F, and then an F2 bar, F3 bar. Yeah, so this is in principle the collision integral that you have to calculate. And of course, if we want to do the Boltzmann equation for the number density, we should multiply, first divide by E, and then you see also the reason why they have these factors here, the 2, because then it just becomes a standard phase space integral. So all the phase space integrals are the same, and then calculate this. So typically, the most important things that you want to consider are dark matter scattering processes. Yeah, so then it's this particle here that is a dark matter particle, and this one here is a dark matter particle as well, while these two are standard model particles. And the other typical process that you want to consider are dark matter annihilation or creation processes, where these two here are dark matter particles, and these two are heat bath particles. So let's first look at dark matter scattering. Yeah, so then we have 3 is also dark matter, and 1 and 2 are standard model or heat bath particle. Yeah, and then when you integrate over this, you just use the symmetry of the process, and you find that this integrated collision operator is just 0. Yeah, so that makes immediately sense intuitively, because, what do we have here actually? It's the time derivative of the number operator, but written in a way that is maybe not so clear. Yeah, so if you write it like this, then you see that the left-hand side of the Boltzmann equation, the Liouville operator, is really just the time derivative of the co-moving number density. Yeah, so that means that whatever is on the right-hand side, the collisions, they will be non-zero if and only if you change the number density, or the number, the number of particles in the collision. But for scattering, of course, the number of dark matter particles before and after collision is the same. Yeah, so it must vanish here. Yeah, and the details are left for you to work out during the exercises. Yeah, so exercise number 1 or 2, I think, will be to actually show this. Okay. So then we have dark matter pair annihilation. Or creation. Yeah, so then, well, one is also dark matter. Let's call it chi, just from now on. And 2 and 3 are heat bath particles. So let's call these heat bath particles psi from now on. Yeah, so now let me also specify what I mean by heat bath. Well, it just means that they are particles that are fully thermalized. Yeah, so that means that I can write, I actually know the phase space distribution of these particles. I don't have to solve for them, because by definition they will follow a thermal distribution. And here I did not include a chemical potential, because, well, at least now for now, I will have in mind the standard model plasma, and their number changing processes are so fast that for all practical purposes you can always neglect the chemical potentials. Yeah, and then again the plus and minus sign, as you know, refers to bosons or fermions. So this is just a like ordinary Fermi-Einstein or Bose-Dirac distribution. Okay, so then just one final thing before we can have a little break. So basically, from this point on, you have to make a few assumptions, and then we will find an expression that I'm sure you've all seen. So first of all, we will assume, or the standard assumption, that we have CP invariance. Yeah, so that means these amplitudes are actually the same. Then we assume detailed balance. So that is just to say that in thermal equilibrium, the entire rates are the same in both directions. Yeah, that's the principle of detailed balance. And then finally, we make an assumption about the dark matter phase space distribution. Yeah, in the end, we want to solve for it, but this Boltzmann equation at the number density level is not sufficient to actually solve it. We need to make an additional assumption. And the typical assumption that is made is that the dark matter particles follow a Maxwell-Boltzmann distribution, up to and over normalization. So you can also say that while we're looking at the limit here where the dark matter particles actually do acquire a chemical potential. And I will motivate this later on. So roughly, or in more detail, so roughly the idea is that these scattering processes will always be very, very efficient, even when dark matter starts to fall out of chemical equilibrium already. So that means that like the velocity distribution will still be that of a thermal distribution, while the number density, so the normalization of the distribution, could change as you drop out of equilibrium. And then from this, and this is again left for you as an exercise. It's one of the standard derivations, and it's very instructive to look at how you use this to start from here. You use these assumptions, and then get at the form of the Boltzmann equation in the way it is most often quoted. So that's then the Boltzmann equation for the number density. So you recognize here the Liouville operator on the left-hand side. So this is really the collision operator on the right-hand side. And you see that, well, there's a part that is proportional to the number density squared of the dark matter particles. Yeah, so this corresponds to this direction here. You have two ingoing dark matter particles, and there's this part that gives you a plus sign, so a production of dark matter particles. Yeah, and the reason, I mean, this is basically this part, so you would naively assume that there should be some standard model number densities here. And the reason that this equilibrium number density is the one of the dark matter particle is because of this detailed balance assumption. Yeah, so we say that, okay, in equilibrium, the annihilation and the creation rates are the same, and therefore I can relate the production to the annihilation in equilibrium. So I should also say that this thermally averaged cross-section, just give you that expression, and then we take a break. So this is the average, velocity average over the cross-section or annihilation rate. So let me just first write this down and then I can say a few words. Yeah, so it's really, you take a look at the cross-section times velocity, and then you average it over the phase-space distribution. Yeah, so here I use the Möller velocity, and that's what comes out of the derivation. Yeah, so I mean, you can't just choose any velocity here. So if you wish, this entire thing is a symbol just that is defined in this way. Yeah, so you have to use the so-called Möller velocity here, and the easiest way to visualize this is it's basically the lab frame velocity. So you put yourself in the rest frame of one of the dark matter particles, and then this is the velocity of one of the other incoming particle. Like sometimes there's also some confusion in discussions, because this is referred to as the relative velocity, and then of course there's always the question of, okay, relative velocity in which frame? Yeah, so the relative velocity in the frame of or the rest frame of one of the particles is not the same as the relative velocity in, for example, the center of mass frame. Yeah, so it's really important to use this one. And that's part of the derivation. I mean, this looks like a rather daunting integral. Yeah, it's a 6-dimensional phase-space integral, but you can bring it down to only one remaining integral. And this is just over the center of mass energies. Yeah, so I integrate here over a rescaled version of the Mandelstam center of mass energy. And then there's this famous expression. Yeah, so this was derived in a seminal paper by Gondolo and Gelmini. Yeah, but it's, again, a very nice exercise to actually do this yourself. So just to explain again, so the variable that we integrate over is the center of mass energy. This x here is a dimensionless version of the temperature, or time, if you wish. Yeah, so x increases as time increases. And then the k's are Bessel functions. First and second kind. And now you also see that, I mean, whatever I said before about the velocity, which sounded maybe a bit, okay, how should I know which one to choose? That's the nice thing about this expression, because in this expression, there doesn't appear any velocity anymore, so there's no ambiguity. Yeah, so you just have the cross-section, and that's how this object here is defined, or comes out of the actual application, of the actual calculation. Okay, so who has seen this form of the thermal average? Okay, good. So that just means that it's a very good exercise to actually derive it. Yeah, because it's super useful, and it provides an actual understanding of what this object here is. Yeah? So intuitively, in words, it's something like this. So you average over the relative velocity times cross-section, but it's actually a well-defined mathematical expression. Okay, so let's take a like 10 minutes break or so, and then I will discuss this equation. And well, probably most of you have seen this equation, so just get from this the standard idea of weakly interacting massive particles as dark matter candidates. Okay, so let's restart. Maybe first with a question, whether there are any questions. Yes. Yes, very good question. Yeah, so we will get back to this. So probably not today, but tomorrow. Yeah, so in words, okay, so this is the argument I will use tomorrow, but very quickly. Yeah, so if you have this process, yeah, so you look at annihilations. On the other hand, you have this process where you look at scatterings. Yeah, then you would naively say, in some like at least vanilla kind of scenario, that the amplitudes are the same. Yeah, could be, for example, a contact interaction. Yeah, but then we are talking about non-relativistic dark matter. Yeah, so the number density of these particles is highly suppressed. It's Boltzmann suppressed, exponentially suppressed, while the number density of these ones isn't. So that means that this rate here is exponentially larger than this one. So that means that as the number changing processes start to fall out of equilibrium, the number conserving processes will still keep equilibrium. Yeah, and that's exactly the rationale for this ansatz. Yeah, but we will discuss in more detail tomorrow. Other questions? Okay, so then let's briefly discuss what this implies. Yeah, so first of all, what is this here? Yeah, the equilibrium distribution. Well, it's just the number density that you will get in full equilibrium. Yeah, so where this is not proportional to, but equal to. So when we actually have a Maxwell-Boltzmann distribution. Yeah, so in particular, then you know that, I mean, you basically have to integrate this over the entire phase space, yeah, to get the number density. And analytically, there are two solutions. So this is just T cubed for highly relativistic particles, and something like, to keep the dimensions correct, something that is exponentially suppressed, as we just discussed, for non-relativistic particles. Yeah, so that means that if I sketch the evolution of the number density, or let me use the co-moving number density, it's easier to discuss because then we know that the left-hand side is just the time derivative of the co-moving number density. So, well, A, the scale factor is, so this is roughly 1 over t. Yeah, so if I use the x-axis as a time variable, or in fact my dimensionless version of time, m by temperature t, yeah, then that means at high temperatures, yeah, when everything is relativistic, this is just a constant. And then we get into this regime where we have exponential suppression at around 1. Okay, so then what does this equation here tell us? Well, like if we want to look at the number density of the dark matter particles, yeah, at very early times, then the equilibrium number density is very large. Yeah, so in general, this will be here term. So this is the annihilation rate, the cross-section times the equilibrium number density. I should compare this to the Hubble expansion rate. Yeah, so as long as this term here is larger than this, I can basically neglect the effect of the expansion of the universe. So I only have to look at this part. So that means I have a change in the number density that is driven by this term. So let's assume that we have a number density that is slightly larger than the equilibrium number density. Then what happens is that, well, there's a negative sign here. So the number density decreases. But if it's slightly smaller on the other hand, this will be negative, so this is positive, so it increases again. And since by assumption this rate here is a large rate, it means that there's a very efficient way of stabilizing the system. So it's an attractor solution. So in other words, the dark matter number density will track the equilibrium density. Until this condition is no longer satisfied. So once we have, well, these two terms roughly the same, so sigma, so 3h roughly sigma v n eq. So then we say that we freeze out. Because then we get into a new regime, then it's basically this term that we can neglect, and it's only the Hubble expansion that is relevant. But of course, if the Hubble expansion is relevant only, then that just means that the collision operator is effectively zero, and we've already seen that this is essentially just the time derivative of the co-moving number density. So also in this case, in other words, asymptotically, we will have a number density that does not change with time. So that just stays constant co-movingly. So this is what will give us our observed dark matter density. Now, if you increase sigma v, it just means that you will track the equilibrium distribution for longer and only then freeze out. So that means that this is like an increasing sigma v. And then from this discussion here, you can basically see two limits. So if you freeze out very early, so in the relativistic situation, then the final dark matter density will not actually depend on the point in time when you freeze out. So this is, for example, the case for neutrinos. So it's exactly the same physics in the early universe that tell you how neutrinos freeze out, but they decouple in the relativistic regime, so their number density does not depend, at least not strongly, on when exactly that happens. But if you freeze out in the non-relativistic regime, which is what we need from the point of view of structure formation, so dark matter has to be cold, we freeze out here, then the number density will very strongly depend on when we decouple. So let's call the point of decoupling xf, and roughly estimate when that happens. Okay, so the condition that we need is this one. So we have very roughly the number density times sigma v. This should be h. Now we are in doing radiation domination. So from the Friedmann equation, we know that h squared is equal to the energy density. The energy density is just the temperature to the fourth. So h is roughly the temperature, and then what enters in the Friedmann equations is the Planck mass. Okay, so on the other hand, we have this number density. So here everything is evaluated at freeze out, right? So the number density at freeze out. Well, how does that scale? Well, the number density of the particles. Afterwards, there are no number changing interactions anymore, so this just redshifts. So I can express it in terms of some number density later on. Yeah, so let's take the time of matter radiation equality as reference point. Yeah, so then at radiation equality, yeah, so I have the density in matter at, so this EQ subscript now refers to matter radiation equality, not to equilibrium, yeah, divided by the dark matter mass. And then, well, it's expanded, so I get a dilution factor like this. Yeah, so this is the equilibrium density in matter, roughly. Yeah, so let's, forget about factors of order unity. Dark matter density should be the same as the ordinary matter density at, as observed today, order of magnitude wise. Yeah, but then, and that's the reason I choose the equality, matter radiation equality as a point of reference here, because at equality, by definition, the energy density in radiation is the same as for matter. Yeah, so this one, in other words, is just T equality cubed. So this is freeze out, right? So why does that not work? Okay, so this is the number density at freeze out. Yeah, so there's a -3, so it redshifts, of course, it dilutes. Okay, so this is roughly then, let me rewrite this. So there's a TF over m chi, then there's the remaining TF squared, and there's a TEQ. Yeah, so this is the radiation density, so that's TEQ cubed to the 4th power, so there's only one factor of TEQ left. Yeah, and now you can compare the two and note that this one, yeah, will be, in practice, we will see that for weak scale dark matter, this happens at a value of maybe 20 or so. So let's, for the sake of the argument, now just call this an order 1 factor. So the main point is that this is basically a fixed factor from the requirement that you get the correct relic density. And then you see that, so this is all at freeze out. Yeah, so then you see that this factor counts as this one. Yeah, so roughly order of magnitudes wise, what we expect is that the required annihilation rate to get the correct dark matter density is given by the geometric mean of the Planck mass and the temperature at equality. Yeah, that's a nice relation to keep in mind, in particular when we talk about like less conventional dark matter production mechanisms, because we will see that there's a very intriguing way of generalizing this, this relation here. So numerically, we can improve on that estimate. And, well, actually solve the equation. And then we see that the dark matter density today is roughly given by 10 to the minus 27 centimeter cubed per second divided by the annihilation rate. Yeah, so it's inversely proportional to the annihilation rate, something which you can directly see in this picture as well. And, well, if you like, to divide out the speed of light here, we just use natural units, then this is very roughly 10 to the minus 10 GeV to the minus 2. And then, well, for the annihilation rate, we can just parameterize this as some generic coupling constant, so some effective coupling constant, and then to get the dimensions correct, we need the dark matter mass squared. Yeah, so then the question is, okay, we know that this should be about 0.1. Yeah, so this one is 0.1. For example, for this effective coupling constant, 10 to the minus 2, and the dark matter mass of around the TeV scale. Yeah, so I say here For example, because obviously this one only fixes the ratio of the two. Yeah, so this actually works also for other combinations. The ratio is strictly fixed by the freeze-out mechanism. But then it's kind of intriguing that you get this ratio for weakly interacting massive particles. Yeah, so if you have particles at the weak scale, electroweak scale, with electroweak kind of cross-sections couplings, you automatically get the right relic density. So WIMPs, yeah, weakly interacting massive particles, more or less generically generate the correct relic density. Yeah, but as I said, as I stressed, it doesn't go in both directions. Yeah? Just from the requirement that you need the correct relic density, you don't know that it's WIMPs. You just observe that WIMP actually get this ratio correct. And this is basically the origin of this reference to a so-called WIMP miracle, because a priori, this is very strange. Yeah? I mean, there's no reason why the electroweak scale should be in any sense related to this cosmological observation. So, yeah, and this was a driver basically for exploring this kind of dark matter candidate. It was also one of the main arguments, in fact, to build the LHC. Yeah? So one was obviously to find the Higgs, but the other one was this WIMP miracle, because it just seemed too good to be true to have an explanation for the dark matter puzzle that is generically related to the weak scale. So, for example, I mean, we have the standard model hierarchy problem. Yeah, so you know that like the Higgs mass gets quadratic corrections. Yeah, so this is basically quadratically proportional to the cutoff mass. Yeah, so in short, the question is why would the Higgs be so small as it is required by measurements? Yeah, so that's a well-known problem, and people have discussed this a lot, and it was part of the motivation why people considered all kinds of modifications to the standard model at the electroweak scale, and that's the kind of new physics that people were or still are hoping to find at the LHC. And of course, there are many good theories. Yeah? So supersymmetry, for example. That fall into this category. So for example, in supersymmetry, it would be the lightest supersymmetric particle, the neutralino. So why do I say good candidate here? Yeah, because it would not only produce the dark matter density generically with the right order of magnitude, but it has been introduced for a completely unrelated reason, namely to solve purely particle physics problems. Yeah, so the hope was in some sense to get the explanation for the dark matter puzzle for free. Yeah, so you introduce supersymmetry, for example, to explain the hierarchy problem, and then you construct your theory and you find that somehow there are these additional particles, neutralinos, and then the lightest of them would be an ideal dark matter candidate. So it's not something that you put into the theory, but that you seemingly got out for free. And that is a very generic thing. So, also other models trying to address the hierarchy problem at the electroweak scale typically contained new particles that you, just needed to make the theory consistent, that satisfy all the properties for these weakly interacting massive particles. So that's why, for at least some time, people took this idea of some sort of a miracle really serious. The other nice thing about the WIMP paradigm is that it's extremely predictive. So WIMP dark matter is predictive. Yeah, so if we have these interactions to a standard model, yeah, then this is basically what sets the relic density. Yeah, but it's something that we could also test today. So even in regions of high dark matter densities in the universe today, in our galaxy, yeah, close to the galactic center, you would expect dark matter particles to meet and create standard model particles, which you could observe then, ideally, as anomalous contributions to cosmic rays. Yeah, and the rates are just such that you could actually see them, or people were hoping this. Yeah, so this is called indirect detection. Yeah, but then there's the opposite direction, where you could produce dark matter particles even today at colliders. Yeah, so also that is something that is actively being searched for. Of course, you can imagine that it's kind of hard to see invisible final states. Yeah, so the kind of things that you're looking for are then monojets. Sorry, not this one, but this one here. Yeah, so you smash together like two protons, for example, and you observe some final states that seemingly violate energy conservation. Yeah, so you're looking for missing energy or missing transverse energy. And then, last but not least, you can look at the scattering of dark matter particles on the nuclei of underground detectors. So this is direct detection. Yeah, so just look for elastic scattering events on the nuclei of some big detectors underground. So underground in order to shield all kinds of cosmic ray contributions. And again, I mean, hopes were really high to find a signal based on the cross-section that we just estimated. And, well, we haven't found anything. Yeah, so that means that, like, vanilla dark matter, vanilla WIMPs, are actually excluded by this. Yeah, so what do I mean by vanilla? By vanilla, I mean, well, basically use the same number for all of these processes. Use the same number to explain the relic density, use our estimate for electroweak cross-sections and masses. Yeah, so basically the numbers that you need in order to really make this surprising, let's call it, if you don't want to call it a miracle. And then you can look at these rates and see it's just excluded. Yeah, so this doesn't work. But then people realized kind of quickly that there are many, many exceptions to this simple story. And these exceptions are not sort of introduced by theorists because they want to keep being occupied, but because they're really rather generic. They appear generically in all these theories that we have discussed. And they are of two types. Yeah, and I put the exceptions in quotation marks because they are not really exceptions. So in some sense, they are very generic. And there are two types to this argument. So one is that the psi's here in this simple sketch are different during the epoch where you set the relic density from today. Yeah, so it could, for example, be that the dark matter couples predominantly to top quarks. It's very hard to produce top quarks in colliders or to annihilate into top quarks today and see the effect. The other option is that the thermal annihilation rate during the time where the dark matter relic density was set is different from the one today. So when should we finish? We started a bit late. Question to the organizer. Okay, because I wanted to just give some examples here of these exceptions, and then it would be a nice breaking point. So let's just look at a few examples. Yeah, so one is something that has been noted very early, that, well, if you have this annihilation rate, you can expand it. Yeah, just a Taylor expansion in terms of velocities. And since we're talking about non-relativistic particles, it's clear that the velocity should be a small parameter. So this should be a valid expansion. And then you can perform the thermal average on this expansion. And of course, well, the average of a constant is still a constant. And then this will be a thermally averaged velocity. Yeah, so it should be the temperature, essentially. So we can express this in terms of this dimensionless parameter x. Okay, so why does that work? Well, depending on the model, depending on the particle physics model, you can calculate, of course, these coefficients. And in some cases, the velocity in the the cross-section in the zero velocity limit simply vanishes. Yeah, so that means that A is much, much, much smaller than B. So then we can take a look at, well, what's today in the galaxy. Yeah, we have typical rotational velocities of 10 to the minus 3, something like 220 kilometers per second. But at freeze out, well, we know that what is the temperature of a non-relativistic particle? This is just 1/3 times the velocity squared. Yeah, so this should be the temperature. I mean, this is expressed in terms of this dimensionless variable, x, at freeze out. Yeah, and then I told you that xf is roughly 20 or so for non-relativistic freeze out. And now we don't have that sketch anymore. In order to get the right Rayleigh density, I mean, this number here depends logarithmically on the dark matter mass. So for a weak scale particle, like 100 GeV or so, the freeze out temperature is around the mass divided by 20. Yeah, so that means that the typical velocity that you get is actually quite high. Yeah, so it's something like 40% or so of the speed of light. Yeah, so that's something to keep in mind when we talk about non-relativistic dark matter at freeze out. Well, it's non-relativistic in the sense that it's not very close to 1, but it's still very, very large velocities. So that means that if we have a model where A is much smaller than B, we can actually have the required annihilation rate during freeze out, but still today, because of this one, the annihilation rate will be much, much smaller. So it's not possible to see these. Just as a sort of footnote, because this is also standard jargon, so sometimes you hear people saying, okay, this is the S wave contribution, and this is the P wave contribution. So don't do that. So like S wave and P wave comes from a partial wave analysis. So S wave means that the lowest order contribution is constant. P wave means that the lowest order contribution goes like V squared. But the S wave contains a V squared contribution. So the B has a contribution from both the S wave and the P wave. Of course, if you have only a P wave annihilation, then it's only B and it's only P wave. But in general, you can't associate like A and B with S wave and P wave respectively. Okay, so what I actually wanted to say about this one, that this is an example where, I mean, as long as you can do this expansion, there's actually a fully general analytic solution. Okay, I don't have quite time to write it down here. It's basically also given an even Colpin-Turner. So there you don't need any fancy tools or so. It's a well understood expansion. But there are examples where you can't do this. And I just want to list a few of them. So another option is that you have a strong velocity dependence other than just a Taylor expansion. Yeah, so this happens, for example, if you have kinematic thresholds. Yeah, so if the mass of the annihilation product of the final state particles, the standard model particles, is close to the dark matter mass, if you have S-channel resonances, but also in the case of non-perturbative effects. So like either you have heard of keywords like Sommerfeld enhancement or bound state formation. These kind of things you can't capture with the Taylor expansion, but they come with an extremely strong velocity dependence. That can result in a situation that today, when we try to probe this, the annihilation rate is much, much smaller than during the time of freeze-out. Other options are so-called co-annihilations. So that's a situation when we have many dark matter particles or dark sector particles. So we have like an actual dark matter particle, and then this is smaller than in mass than some, let's call it chi2, and so on. So we have many, many particles that share some common symmetry. So in supersymmetry, this would be R parity. And then you basically get a coupled system of Boltzmann equations of this type. But you know that in the end, all of these particles will decay to the lightest particle, the lightest neutralino in the case of supersymmetry. And it turns out that you can you can compress the system of coupled Boltzmann equations into a single Boltzmann equation for the sum of the number densities of freeze-out. That takes the same form as this one, just that this annihilation rate here becomes an effective annihilation rate that sums over all possible annihilation processes of all these particles, weighted by some thermal factors. Long story short, it's again an example where the annihilation rate of this lightest particle, the one that we could potentially observe today, might be very small compared to the annihilation rate of the other ones that effectively sets the dark matter density. Okay, so then we have asymmetric dark matter. So we might have a situation where dark matter is not self-conjugate, such that the number density of dark matter particles and anti-dark matter particles is not the same. And this is not a crazy idea at all if you think of the standard model. So in the standard model, it's not this process that sets the relic density of observed matter as opposed to antimatter. So the reason that the universe consists of matter rather than antimatter is that there's an initial asymmetry. So the annihilation rate or the cross-section of matter antimatter annihilation in the standard model is huge. So if ordinary matter was produced by this mechanism, the matter content of the universe would be by many, many orders of magnitude smaller than the observed one. So it's an entirely different mechanism. Basically, you annihilate away all the antimatter contributions such that only the residual asymmetry is left. That could also be the case for dark matter, explaining why we don't see any annihilations today, simply because there's no anti-dark matter around. And just one final example is that you could have this entire process also in a completely secluded dark sector. So what do I mean by that? Well, so far my psi's here were standard model particles, part of the standard model heat bath. But you could imagine that these are new physics particles, BSM particles, that are not charged under the standard model gauge group, just as the dark matter particle, but that somehow thermalize in the early universe with itself. Then you would have a separate thermal bath, and this is a model building direction that has been much discussed in recent years as well. Because the same mechanism works in exactly the same way, but of course you can't directly observe this because, well, we don't there's no easy way of producing these dark sector particles. Okay, so just as I say here that there are actually analytical solutions, the whole point of listing all these things is that, okay, A, it's really interesting from a model building perspective, but B is that there's no way around that you actually need like accurate numerical tools to solve this equation then. There's no way to do this analytically anymore. So here we need a numerical treatment. And then there are many public tools that do this. So for example, Dark SUSY, there's Micromegas. MAT DM. And that's also one of the reasons why we want to at least partially address this in the exercises as well. Because for any realistic model, if you want to match, and that brings me back to the start of the lecture, if you want to match the accuracy of the dark matter observations, density observations that we have today, you really need to use like high-level codes like this one. And just to add, the SUSY here is not really SUSY at all anymore. So that's more like a historical reason for the name. So of course you can do any kinds of dark matter model calculations. And it's actually, I mean, all these effects are fully implemented. And that's something that you will start to explore, not in the exercise today, but in the next exercises. Okay, so sorry for taking too long, and enjoy the lunch break.